Hi, my name is Drew Griffiths, and this is my presentation for Physics 2212 Lab 4 Magnetic Field of a Bar Magnet. So the purpose of this lab is to measure the magnetic field of a small bar magnet at various distances from a magnetometer. And we use this by downloading a magnetometer app on our phones and finding the location of the magnetometer sensor in our phones. And I'll detail that process later in this video. And we calculated the magnetic field using the on and off axis magnetic fields. And some quick results are the N equals negative 2.48, and the magnetic dipole moment, or mu, equals 4.42 A times meters squared. And here are the fundamental physical principles that were used in this lab. So first is the Biot-Savart law, which relates the magnetic field at any point to a tiny current element. And then next, the magnetic field of a dipole. And a magnetic dipole is a closed circulation of an electric current system. And then the distance dependence formula, it's just pretty much states that the magnitude of the magnetic field due to a bar magnet falls off with distance, and this is proved later on in this lab. Okay, here's the procedure for our experiment that we did in this lab. And so first we oriented the phone so that the magnetometer points in the direction of Earth's magnetic field, so that Earth's magnetic field will not have any impact on the magnetic field of the bar magnet in our measurements and screw up the procedure. And to find the location of the magnetometer chip in the phone, we first moved it up and down to find where it was on the y-axis, and then we put a tape on there, and then we turned the phone sideways and moved it horizontally to find where the magnetometer chip was in the x direction, and we put another piece of tape there, and where the tapes intersected was where we determined the magnetometer chip to be. Now here is our data for the on-axis portion of the lab. So on the left here, you can see the distance of the bar magnet from the magnetometer chip and the approximate magnetic fields at these distances. And this checks out with the distance dependency formula, because in the graph you can see here, as the distance gets further away, the magnitude of the magnetic field gets lower, and that is corresponding with the distance dependency formula like I just mentioned. And here is the results for our off-axis data. So this is a similar procedure to the on-axis data, but instead we moved it a perpendicular distance in the vertical direction from the bar magnet, and then calculated the B field, the magnetic field at this point as well at various distances. And as you can see here, here are all the distances and the magnetic field data that we calculated. And here is the first little part of my GlowScript code that I'm going to be showing you. So pretty much this is just showing the initial conditions where we set mu equal to 4.42, which is the value that we calculated earlier in the lab. And here is the second part of the GlowScript code that I was going to show. And as you can see here, we set the dperp equal to be 0.19, which we found during the off-axis part of our experiment. On the left here, you can see the results from the GlowScript model of our experiment. So then some of the assumptions / errors that we made in this lab was, first, based on the distance dependency formula, the magnetic field falls off as distance increases. So the magnitude of the magnetic field decreases as distance increases, and this was proven in both the on-axis and off-axis portions of our lab. The second assumption we made was that the bar magnet acts as a magnetic dipole, and one error was that other magnetic objects could skew the data, such as computers or other electronic devices that were close enough and their magnetic fields impacted the magnetic field of the bar magnet. And lastly, the exact location of the magnetometer was not exactly found because it's just an estimate with the two pieces of tape. Then our conclusion questions: what if we hadn't compensated for magnetic north and placed the meter stick at an intermediate angle relative to the Earth's magnetic field? Then the Earth's magnetic field would impact the magnetic field of the bar, affecting our results. Then if we connected two identical magnets end-to-end and repeated the experiment, then the magnitude of the magnetic field would double, but the direction would stay the same. And that's all. So thank you for watching.